Hello, my name is Michael, and I am an iOS engineer for the measurement team for Zozo Technologies. So today I'm going to talk about Stack Overflows in Swift. I'll be covering why we're talking about the stack in Swift, what the stack is, how the stack is used in C, and then we'll do a tour of the stack using the LLDB debugger. We'll then look at stack usage in Swift, and then what is a Stack Overflow, and then we'll look at some Swift Stack Overflow examples and how to prevent them. So first of all, why talk about the stack in Swift? Well, when I was working on the Zozo Glass project, we had a Stack Overflow bug. Now, at the time, we didn't know it was a Stack Overflow. Overflows are not obvious in most cases. And with the case of Zozo Glass, it disappeared with optimized code. So we'll see why that's common in a second. So once we figured out what the problem was, it was a fairly trivial fix, but it made me realize that Stack Overflows, even when using a very safe language like Swift, are something that every programmer should really know about. And especially with Swift, overflows can easily occur when interfacing with C or C++ code. Swift hides many of the details of the stack, so the only real way to figure out what is going on is to take a look at the assembly under the hood. So first of all, what is the stack? Well, the stack is a fundamental program construct. It is an automatically managed piece of memory, and it is in a last in, first out data structure. Now, in the case of Mac OS, the stack is a piece of virtual memory, and it starts at high addresses and grows towards lower addresses, like so. Now, each frame on the stack is generally a reference to the scope of a function. So when we enter a new function, we effectively establish a new frame on the stack. It doesn't have to be this way, but that is the general rule. Now, the stack is 100% managed by the compiler, and its usage is fixed. There is very little reason to change that. And function calls from the stack, they must adhere to the OS ABI, which in the case of Mac OS is System V AMD 64. So for this talk, I will be using Mac OS for all of my examples. So let's look at a very simple example of the stack usage. So we have a program on the left. It's extremely simple. It's a C program, and we have, like all C programs, they must start with a main function. So in our main function, we simply declare a variable A, assign 3 to it, and then we multiply it to get the cubed value of that variable. We then print it with a formatted string. It's a very simple program, and if we run the clang command here, we're able to output the x64 Intel assembly. So what does that assembly do? I've created a little debugger, sort of virtual debugger here, where we have the assembly from the previous program here on the left, and the pink arrow is an instruction pointer. So it points to the instruction we are about to execute. Up here, we have the relevant LLDB commands for that instruction to find out what is going on in the registers of the memory. On the right, we have the CPU registers and what value they are showing at that instruction. And then below that, we have the stack memory itself. So as you can see, we have the addresses on the left and what is contained in the memory on the right. At the moment, there is nothing. So before we even get started, there are two very important registers I must detail. Those are the RBP and the RSP register. So the RBP register it simply means base pointer, and it indicates the start of the current stack frame. RSP indicates the end of the current stack frame, and SP just stands for stack pointer. So in this case, before we've even executed a single instruction, we can see that some stack space is already reserved. And this would be from the previous frame or the frame that is calling into our main function. So the first thing our main function has to do is establish a new stack frame. First, we do that by pushing on RBP. What pushing on RBP does is it takes the value of the current value of the RBP register, and it copies it onto the stack. It has to move the stack pointer down 8 bytes in order to do so, because a memory address on a 64-bit system is 8 bytes. Now, the reason we do that is because we are going to overwrite the old RBP with our new base pointer. So to establish that new RBP, we simply just copy the RSP, the current stack pointer, into the RBP, and that's what this instruction does. As we can see, it has copied the RSP into the RBP. Finally, we have to reserve some stack space for our frame. So we simply do that by subtracting from the current RSP. Now, in this case, we're subtracting 32 bytes, and when we execute that instruction, you can see that the RSP has moved down 32 bytes, and we now have this gray area which represents the stack that we can use for our function. I won't go into too much detail with these 3 instructions here, but all they do is copy the arguments to the main function onto the stack. This is unoptimized code, and we don't actually use those arguments, but because it's unoptimized, it does it anyway. Next, we get to the meat of our program. We copy a constant 3 onto the stack too. Now you can see here with this dword pointer, and then in the square brackets an RBP minus an offset, we can see how we refer to the stack. So that's simply just saying copy a value or move a value, this constant value, into the stack, starting at RBP minus 20 bytes. So in this case, this should be the next slot available on the stack here. And if we step through that instruction, we can see a 3 has been moved onto the stack there. Then we move that 3 back into a register, in this case, the EAX register, and then we multiply it twice. So now we can see that the EAX register contains the value 1B, and that is just hexadecimal for 27. So that's our cubed value. I won't go too much into the next few instructions, but essentially they just set up our registers so that we can call into the printf function. So you can see before we call into the printf function, we have a string pointer that has been loaded into the RDI register, and that is just pointing to our formatted string, which is cubed, and it takes a format for an integer. The integer we pass into that is stored in the RSI register, and that's just our 1B or 27. So this is part of the OS ABI. The arguments that are passed to functions must be defined in a specified order. And in this case, we start with RDI and then RSI. So then we call into printf. We're not going to step into that because it is actually a very big function. But when we call it, there are 2 things that are worth noting. First is that our EAX register has been filled with the value 9. So that is the return value from our printf function. And once again, that the fact that it returns into the EAX register is part of the ABI. And that just indicates the number of characters we printed. Secondly, if we print out the RSP, the value for the RSP register, we notice that it's exactly the same. It hasn't moved. Now, when we called into printf, undoubtedly printf used a lot of stack space. But the important thing to note is that when we step over it and the call to the printf has finished, our stack is in the exact same state as before we called it. So our RBP is in the same place and our RSP has not changed. That's a very important fundamental operation of the stack. I'll step over the next few instructions because they're not too important, but all they do is move the value 0 into the EAX register. And once again, the EAX is part of the ABI. It's defined as part of the ABI as a return value for a function. So if you remember C programs, if you return 0, that effectively indicates that the program completed successfully. So that's why we're copying 0 into EAX. Finally, but very importantly, we then need to return the stack back to its original state. So we do that by adding 32 bytes back to RSP. And we can see now that our stack memory is effectively invalidated. It's still there, but we wouldn't want to refer to it because it could be overwritten at any time. Finally, we pop on RBP, and that just does the exact opposite of push. It takes the value, the 8 bytes at the RSP, moves it back into RBP, and then it steps the RSP up 8 bytes. So if you'll note here, our state, or the state of our stack, is exactly the same as when we started, which is very important. Finally, we return from the function, and that just returns to the calling frame, which in this case is probably LLDB. It's an LLDB dynamic library. So now that we know how the stack works in C, let's take a look at Swift. We have the same program here on the left. We declare our variable A, and then we cube it, and then we print out the result. If we run the Swift C command up here, we're able to output the x64 assembly. And the first thing to note is that it gives us 1,200 lines of code. Now, there are many reasons for that. Most of them, they sort of fall outside the scope of this talk. I really just don't have enough time to talk about them, but I'll get onto that in a second. More importantly than that, though, we want to know what is being done with the stack. So just like our C program, we have a main function, and we push on RBP to establish a new stack frame. We then move RSP to RBP to set up the new RBP, and then we subtract from RSP to reserve some stack space. So in this case, the subtraction is probably the most important instruction. As we can see here, we're taking up 152 bytes for our stack, which is a lot more than what C uses. Now, the reasons for that, once again, I won't go into them too much, but there are some reasons written here. I'm not going to go into them into detail because they're not really that relevant to this discussion. But for those that are interested, there is a link to the source file, that assembly file here from GitHub that you can take a look at. It's also worth noting that when this code is optimized with the -O argument, it reduces the stack size to about 40 bytes. And the C version with the O-fast argument reduces it to about 0 bytes. So that's quite a big difference, 152 to 40 bytes. And that, I hope you can start to see why that optimized builds might fix any Stack Overflow errors, or to put it another way, unoptimized builds are more susceptible to Stack Overflow errors. So with that, we should be able to explain what a Stack Overflow is very easily. So Stack Overflow is just caused by out-of-bounds stack allocation access. So as we know, the stack grows down towards lower addresses, but it's just an allocation, like any allocation managed by the OS. So if our stack grows too large, we step off the end and we try and access memory that is not allocated by the OS. Because it's just an allocation, we don't get any specific Stack Overflow error. We just get an exec bad access error. And that can make it very difficult to figure out if the error we're dealing with is a Stack Overflow or not. And as said before, you can imagine why with optimizations, the Stack Overflow errors could disappear because the frame sizes are smaller and we don't step off the end of our stack allocation. Now, a good way to cause a Stack Overflow is with recursion or by declaring lots and lots of data on the stack itself. And with Swift, that's usually with large structs or tuple declarations. And we'll look at some examples of that now. So here's a very simple example, and it is guaranteed to cause a stack overflow. We simply recursively call back into a function. It's a very simple function. And this is obviously very bad programming practice, but we can see, if we look at the assembly, we can see why. So we have our mangled function name at the top. We then push RBP and we set up our new stack frame, and then we sub from RSP 32 bytes. So effectively, we have established a 32-byte stack frame here. We do a whole bunch of stuff in here, and then finally, we call back into ourselves. So when we call back into the function here, all it does is it moves the instruction pointer back to the top of the, back to the first instruction here. So you can see quickly that we are going to continuously subtract from our RSP and continuously increase the stack size used. So we never ever get to this point after the function where we are able to give that stack space back. So effectively, we just keep calling. It's effectively just an infinite loop. So eventually, we'll get to a point where one of these instructions will try and access the stack, and it will throw an error. And we can see here, if we run the program, that's exactly what happens. We get an exec bad access. Now, if we subtract the current RBP from the initial RBP, we can find the rough stack size used. In this case, it's about 8 megabytes, and that is very close to our actual stack limit of 8 megabytes on Mac OS. Next, we have another simple example, this time where we declare a tuple on the stack of 32 bytes. And we keep recursively calling this function until we are able to declare 8 megabytes worth of tuple on the stack. So this creates 2,200 lines of code, assembly code, so we won't go into all of that. But once again, the most important thing to note is that at the start of our function, we effectively reserve some stack space. And in this case, it is 600 bytes of stack space, which is a lot. So lo and behold, when we run our program, we get a segmentation fault. This time, we've only used about 400K of the stack for the actual tuple. So this doesn't come anywhere close to our 8 megabyte limit. And that's because Swift is using a lot more stack. So how do we prevent that? Well, the previous example is exactly what happens when we use C structs with fixed size arrays on the stack. Normally, when we declare them, that just uses that stack space. So the easiest way around it, and the way we fixed the problem for Zozo Glass, was to declare the stack as a part of a class, a larger class wrapper. That way, when we declare that class on the stack, only the reference is stored on the stack, and the rest is allocated in heap memory. Now, secondly, if we have a recursive function, we should get rid of it. There's really no reason to use recursive functions, and they can be replaced by while loops. So here is an example of a recursive function that would fail, but the while loop that would work okay. And in this case, it's important to note that tail call optimization will probably make this work in an optimized build, but that's very bad practice, and we don't want to do that. Finally, some other tips. Never use a pointer to stack memory outside of the function scope. So hopefully it's obvious why that is now. Swift makes that difficult, of course. Now we can use thread.stackSize to check the available stack space. However, there should be no reason to increase the allotted stack size. If you have to, then there's probably something you're doing wrong. There's probably a better way to do it. If possible, don't use fixed C struct arrays. Now Swift has a tuple size limit, and it makes for long compile times. And finally, it's worth learning the assembly to understand the usage patterns. Now, that's all for my talk here. There's obviously a lot of more information, and if you look at the appendix, there are a bunch of slides that contain more information if you're interested in finding out about more. Finally, there are some links, and if you have time, I thoroughly recommend you check out the talks at iOSDC from my fellow Zozo colleagues. Thank you very much.